use the coordinate plane to help us graph real-life data and make predictions and see patterns with it. And when we use real-life data, it's called a scatter plot. Scatter plots normally help us to see trends, but what's different from a scatter plot than maybe some of just in the past when you've done just graphing points is scatter plots are real-life data, and real-life data usually does not lie in a perfect line. So let's look at this example. It says you want to know the distance that 5 tires with different diameters, d, cover in one revolution. So how much distance they cover every time they go around once. Your estimates of the circumference, c, that would be the distance around the tire, how much they go around, are given in the chart. Use a scatter plot to find the incorrect estimate of the circumference. So basically what this chart is saying is that if a tire had a diameter of 48, so its distance across of this bad circle here and this bad line, let me try that again. The distance across is 48. And we're estimating that around this, its circumference would then be 151 inches. You know, if the distance was 23, our circumference, the distance around, was 72. So it's telling us here that there's going to be an incorrect estimate. But by graphing this information, we could see if we had done something wrong. So let's graph this on a coordinate plane. So I've sketched a coordinate plane here. Again, we're dealing with our x-axis and our y-axis. But in this case, we're going to deal with our independent variable, our d, okay, because we measured all the tires, and we're going to see how that diameter affects our circumference. So our independent variable, our x, is going to be this d on this line, on this axis, and our circumference we're going to put on the y-axis. Okay, so we can, if you want, label this diameter in inches. I believe we're measuring everything in inches. And along the side here, we can have circumference in inches. Okay, and then all we're doing, ladies and gentlemen, is we're plotting these points. Now if you can't see the points, this right here becomes the point 48, 151. This is the point 23, 72. So if you look at our d values here, our independent variables, you see that our least value is 20 and it goes up to 48. So if I want to graph these, you don't have to start at 0. I'm going to warn you, as we talked about in the past, if you don't start at 0, it might skew the data. But it's helpful to put in a bar break and saying, okay, my values start at 20, that's a nice round number, I'm going to start here at 20. And I have to go up to 48. So again, you could go by 5s, I might try going by 2s, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, and then this would be 50 here at the end. Okay? And for our circumferences, it seems like we start at 63 and we go up to 151. So again, I'm going to put in a bar break, and I'm going to start at 60. It's pretty close to 63, and I'm going to go by 10s. 70, 80, 90, 100, 10, 20, 120, 30, 150, I'm sorry, 140, and then this would be 160 up here. Okay? I don't have to label every line as long as I tell you the scale I'm going with. Okay? And again, we put bar breaks in because there's more data up here, or in between 0 and 20, between 0 and 60. We're just not using it. So we plot the points. The first point we have to plot is 48, 51. So 48 is going to be over here, and 151, I'm sorry, is going to come all the way up. Here's 150, so it's going to be just past that. And you just put a dot there. Our next point is the point 23, 72. So 23 is going to be here, 72 is going to be right in here. Okay, again, scatter plots, we're just doing our best that we can do to put a point that represents these numbers. This point, 20, 63. 20, 63 will be right in here. 24, 130. Here's 24, 130 is way up here. And we have 30, 94. Here's 30, 80, 94 would be right in here. Now, as I'm looking at this information, remember it told us to use a scatter plot to find the incorrect estimate of the circumference. If I'm looking, you can see that most of this data falls on a pretty straight line. What that's saying is as the diameter of our tire gets bigger, the circumference gets bigger. Makes sense. Except we have this crazy one right here. Okay, it doesn't seem to fit in the rest of the data. So I'm guessing that our incorrect estimation is going to be the one here at 24, okay, because that doesn't fit with the rest of the data. So the incorrect estimate is going to be 24, a diameter of 24 inches does not go along with the circumference of 130 inches. So our incorrect circumference is going to be the 130. Okay? Again, that would be hard to see from here, but when you put it on a graph, you're able to see what doesn't make sense. Let's look at another example. In this one it says the number of U.S. citizens 7 years or older in millions who played soccer is shown below. Draw a scatter plot, describe the pattern, and predict the number of U.S. citizens who will play soccer in 2007. Again, a great thing about creating scatter plots is we can make predictions. So it gives us the years and how many people in millions played that sport. Okay, so again, let's set up a scatter plot. I'm going to put years along the x-axis, and I'm going to put the number of players along the y-axis. So if we look at our years, we're dealing with 1, 2, 3, 4, 5, 6 years, and each one has a difference of 2 years. So we're really going by twos. Okay. With time, you don't necessarily need to use a bar break because it's pretty self-explanatory. So my first year I'm starting with is 1987. So I'm just going to start like right here. This is going to be 1987. And I'll say this is 1989. Then this is going to be 1991, 1993, I hope I'm doing this correctly, 95 and 97, and 1997. Okay. And so these, of course, are our years. Important to label the graph so we know what we're talking about. And we're also dealing with the number of soccer players. Okay. So maybe we want to just call this over here number of soccer players. You can call it whatever you'd like. Now remember, this is done in millions, and it's important to list that because otherwise it's going to look like we had 10 people play soccer. In millions. And if we look at our scale here, it seems like we're going from 9.8 million to 13.7 million. So again, we can use a bar break and maybe go by 500,000. What I mean by that is maybe start at like 9.5 million, 10 million, 11 million, 12 million, 13 million, 14 million. Okay, so each one of my lines represents a 500,000. 9.5 million, 10, 10.5, 11 million. Okay, so now we can plot our information once we have it set up. In 1987, there were 9.8 million people who played. So 1987, here's 9.5, here's 10, so it's going to fall somewhere in here. In 1989, we had 11.2. This will be just past the 11. In 91, we had 10 million. In 93, we had 10.3. 10.3, 10.5, so right in here. In 95, we had 12 million. And in 97, we had 13.7 million. That's going to be up here. So looking at the data, we can see, I'm going to describe a pattern. Okay, we can see that the trend really is to increase. Okay? In fact, we increased every year with the exception of this year. This was the only year we actually went down. So we had like a lull here. Okay? So if we want to make or describe the pattern, you might want to say something with the exception of 91 where we went down. Okay, with the exception of 1991, participation again, apologize, I'm writing so sloppy, increased. Oops, writing sloppy and can't spell. Increased every year. That would be one conclusion, one thing we could say with the pattern. Okay. So with the exception of 1991, participation increased every year. Okay, even though here didn't jump as high as this one, it still increased. The second part says, predict the number of U.S. citizens who will play soccer in 2007. Well, what's happening every single time? And maybe I should have made my graph a little bit bigger so I could go out to 2007. Because this would be 1999, and this would be 2001. Okay? But if you look, we're kind of increasing, right? Okay? So in about 2001, I'm expecting, if I were to draw what we call a line of best fit, and we'll talk more about that later. Okay. This line kind of represents the data. Now I'm expecting in 2001 for it to be over 14. So in 2002, maybe hitting 15. So in 2003, maybe hitting 16. Sorry, I'm sorry, we went up by 2. In 2003, maybe hitting 15. Okay. 2003 be out here, and again, I apologize, didn't make my graph big enough. So if we said like in 2003, we expect maybe to hit around 15 million. 2005, maybe at another million, 16 million. So maybe in 2007, approximately 17 million. Somewhere in that. Now it's hard to tell again without extending my graph further. And I again apologize for spelling a word wrong. But we expect it to increase. And so we expect it to be higher than it was here. And from our graph we can see that, you know what, it's going to keep going up. Like this one jumped here 2 million, but really it seems to be going up close to 1 million every year approximately. So a best guess we could have would be 17 million. And we can use our graph to see that. If our graph was going down, we'd know it'd be decreasing every year. But again, scatter plots can help us see real life information and make predictions about what's going to happen in the future.